This is Calculus 3 lecture video number 23 on triple integrals. Now, we've previously evaluated single integrals of functions of a single variable where we had y equals f of x. And then we took it to the next level and we evaluated double integrals of functions of two variables where z was a function of x and y. So now we want to look at integration of functions of three variables. Typically we use w to represent a function of x, y, and z. And as you might expect, then this is going to involve triple integrals, such as the following. So you would have the triple integral over, and notice here the subscript is e, representing the three-dimensional solid, which is going to represent our region of integration. And then your function is the integrand f of x, y, z, and then dv. So let's start by supposing that we're integrating over a rectangular solid to talk about what the process is going to be, and then from there we'll generalize as to how to integrate over other kinds of solids. So as always, when we talk about how to set up our idea for integration, we cut the solid into small pieces, which, if we're assuming it's a rectangular solid, these are going to be small rectangular solids. Now, each piece has volume given by delta V, which can be found by taking delta X times delta Y times delta Z. So what do we do next? Well, we choose a point in each piece, and that point we'll call X sub I star, Y sub J star, Z sub K star, and then you evaluate your function f at that point. And then from there, you would take the function values times the increment of volume. So that would be times your delta V. So times the increment in volume. So you would add these all up. So you would take the sum, k equals 1 to infinity, sum, j equals 1 to infinity, sum, I equals 1 to infinity, f of x sub I star, y sub j star, z sub k star, times your delta v. So basically this is adding them all up. Then you take that limit, and you end up with your triple integral over e of f of x, y, z dv. All right, what does this triple integral represent? I'm sure you're curious because we're familiar when we integrate a function of a single variable over an interval, it represents the area under its curve, or we saw some double integrals could represent volumes or areas, but what would a triple integral represent? Well, one application or idea is if your function is a variable density function for some object, then the integral represents its mass. Okay, but at times if you don't have something so specific, then really this integral over a solid would represent a four-dimensional quantity, which is hard for us to understand. Okay, so we're going to start off, we're going to evaluate this just using rectangular coordinates for this lesson, and then we'll see what other coordinate systems we can work with for triple integrals in future videos to come. So let's look at an example here. We're going to evaluate the following triple integral. My integrand, my function is 2xy, and then notice the order of integration is dz dy dx. So these outer limits always have to be the constant ones, right? And they apply to x. Then the next set of limits from x to 2x apply to y, and then this last set of limits apply to z. So that's what I'm going to anti-differentiate with respect to first. All right, so I'm going to leave alone the 0 to 1, the x to 2x, and then if I anti-differentiate 2xy with respect to z, well, 2xy is just a constant, so I'll have 2xyz evaluated from 0 to x plus y, and then I still have dy dx. All right, now those limits get plugged in for z, because that's what I anti-differentiated with respect to right now. So we're going to have integrals 0 to 1, x to 2x, 2xy times, and substituting in the limits for z, I'm going to have x plus y minus 0 dy dx. All right, not too bad. Now let's just distribute across this 2xy. So we'll have integral 0 to 1, x to 2x, and then we have now 2x squared y plus 2xy squared dy dx. And then in this next step, now I'm going to anti-differentiate with respect to y. So I'm going to treat x as a constant. So we'll have integral from 0 to 1. Let's see here. So if I'm treating y as my variable, antiderivative is going to be y squared, and then I'm going to divide by 2. So that'll cancel out. So I have x squared y squared plus, and then this y squared is going to become y cubed, and I need to divide by 3. So I have 2xy cubed. I'm going to evaluate this from x to 2x. And then lastly, don't forget your little dx. Okay, from here, I think you guys have it under control. So you should end up with 23 over 15. Nice. Now, let's talk about orders of integration. So we saw that with double integrals in rectangular coordinates, we had two options for setup, right? It was either dx dy or it was dy dx. But for triple integrals, we're going to have 6 different possibilities. Let's list them out. So you could do dx dy dz, or dx dz dy, or dy dx dz. You get the point, right? Then you could interchange those last two, or you could have dz on the inside and then dx dy, or switch the outer two. Now, as before, if the limits are all constants, then the order of integration can be interchanged freely. But it's often important to take time to examine the region carefully in order to select the order of integration. And so we have 3 different orientations or types of solids, and this will help you determine what order of integration is best for the problem at hand. So say you have a type 1 solid whose base you can see is most easily defined in the xy plane, right? So E is the solid, but the base of the solid is in the xy plane, and then its height can be determined as functions of x and y. Well, then in that case, the way you would want to set up your triple integral is to have the innermost, or the first iterated integral that you compute, be the ones with respect to z. So you would have u sub 2 as the upper limit. That says u sub 2 of xy. And then this is u sub 1 of xy. That's determining the bottom. So if you take the difference between the two, that'll give you the height of it. So u sub 2 is the upper limit, u sub 1 is the lower limit. And then the outer two, you would get those limits from the region D. And so you would have dz first, and then you could either do dx dy, or you would have dz first and then dy dx. It really depends on D, which of these two orders you do, dx dy or dy dx. All right, and then if you take a little closer look, so you have a triple integral of just dv, what do you think this would give you? It gives you a volume. And if we take a look at how we set it up for this type 1 solid, so you would have double integral u2, u1, dz, and then dx dy or dy dx I'll just represent with dA. And then if I anti-differentiate here with respect to z, I'm just going to have z evaluated from u1 to u2 dA. And then, like I said, the difference in those two values gives you the height, right? And if I substitute them in for z, that's precisely what I get. And then that's a familiar double integral. Okay, now let's look at the other solids. We're not going to do such a rigorous setup. We'll just talk about which one you would anti-differentiate with respect to first. So if you have a type 2 solid, notice D, the base this time, is in the YZ plane. So what would you integrate with respect to first? You would integrate with respect to X first. And notice X is a function of Y and Z. So X first, because it depends on Y and Z. And then lastly, if you have a type 3 solid where the base is in the XZ plane, then you would integrate with respect to Y first. All right, don't worry about memorizing like if it's type 1, 2, or 3. Just understand how to set it up. All right, now let's dive in and look at some examples. So set up the triple integral over E of x dz dy dx if E is the first octant solid bounded by the coordinate planes and this plane here. And then they want us to set up another triple integral, and this time you see the order of integration switched around. So let's first draw this solid, and the way the order is given to me in the problem, I'm going to use the xy plane as the base region because those are the outer two variables that I'm going to integrate with respect to. So I'm just going to draw this in the first octant. They told me it's a first octant solid. So zxy. And then let's graph the intercepts of this plane here. So x-intercept is going to be 2, y-intercept is going to be 3, z-intercept is 6. All right. So there's the plane. The base, notice, is in the xy plane. It's determined by this triangle here. And then the heights are determined by the plane's equation. So the limits for z, you can draw that arrow again in the z direction. It would start at the xy plane and end at the equation of the plane. Maybe it comes out to here, something like that. Okay, so what I recommend is we're going to draw the xy plane separately, the base region, so we can figure out what the limits should be for D, and then we'll put it all together. So x-intercept was 2, y-intercept was 3. So here's our little triangle. This is the base region, this is D. Okay, well this equation here, that's a line, y-intercept is 3, slope is -3/2. So now we're ready to roll. It makes sense, let's put our constant limits for x on the very outside. So we would have integral from, in the x direction, 0 to 2, in the y direction, 0 to 3 minus 3/2 x. And then in for the z limits of integration, remember those purple arrows? So they started in the xy plane, which would be where z is 0, and then it stops at the equation of this plane here. Well, the equation of the plane is z equals 6 minus 3x minus 2y. And then we're integrating x, and the order was dz dy dx. All right, and notice all they asked me to do was set it up. So we're done. What a relief. Will it do a rectangle? Yes. Okay. Now they want us to set it up and switch the order of integration. They want us to do dx, dz, dy. So what does that mean for us? Well, it means now I'm going to treat the yz plane as the base region for the solid. Okay, so let's see what's going on in the yz plane. I'm going to draw it separately again. So we'll say this is the z-axis, and this is the y-axis. And now look here, the y-intercept was at 3, and the z-intercept was at 6. So here's what's going on in the yz plane for the solid. And I'm going to treat this as the base of it now, okay? All right, well, what's the equation here of this boundary? This would be z equals 6 minus 2y. And we're going to have our outermost limits representing y, so those are going to be constant. So it'll go from 0 to 3 in the y direction, 0 to 6 minus 2y in the z direction. And then now you're going to have to kind of turn your head sideways. So the plane is still going to determine the height, but you have to solve for x, right? So you're going to go from 0 up until, now if I solved for x in the equation here, I'd subtract the 2y and the z over and divide by 3. So you would have 2 minus 2/3 y minus 1/3 z. And then you're integrating x with respect to x, and then z, and then y. So that's the other option. It's not like one's going to be much better to evaluate than another. All right, so basically the idea is always draw that base region first so you can set up those limits and then focus on that third iterated integral. All right, let's look at another example. Rewrite the given iterated integral in each of the 5 other possible orders. All right, so notice they're not actually telling us what the function is that we're integrating. We're just setting up all the different versions. So they've given us 1, there's 5 more, right? There's 6 total. So notice here, these outer limits are for x. X is ranging between -1 and 1. And then the next set of limits from x squared to 1 represent the limits on y. So y is from x squared to 1. So I'm just going to draw out what's going on in the xy plane first so we can understand. So here's the xy plane. So the limits for x are from -1 to 1. And then lower limit for y is x squared, and upper limit is 1. So that means it's bounded below by this parabola and above by the horizontal line y equals 1. So that's what the base of our solid looks like. And then now let's throw z into the mix. So this is z equals 0, which would be the xy plane. And then z equals 1 minus y. So that's another plane as well. That's bounding the solid from above. So now it's time to put everything together. Let's draw in 3 space what this solid looks like. So I'll extend the x-axis because it goes to -1, but no need to have negative values on the other axes. So here's the x-axis, y-axis, z-axis. And then x goes between 1 and -1. Y goes up to 1 as well. So remember the base was that parabola. Right, that's our xy plane picture. And then notice the solid is bounded below by the xy plane. Okay, got it. Maybe I'll shade this in. Okay, and then above by the plane z equals 1 minus y. So just draw that as a line in the in the yz plane and then extend it parallel to the x-axis. So here's 1, and it would have intercept at 0, 0, 1 as well as 0, 1, 0. And then imagine this plane is coming out in the parallel to the direction of the x-axis. So if you were to create a solid, what would it look like? It only lives above this parabola. It's going to look something like this. So you have also, this is like a face of the solid coming towards us. And then this portion here, this is flat, 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 flat. The plane cuts it. That's getting a little too dark, hold on. I want a more gentle color. Maybe this yellow will be gentle. Oh, nice, okay. All right. Good, so that's our solid. So let's start off with the easiest next ordering of integration. I'm just gonna switch up x and y, okay? But that means I can leave that innermost integral the same, the 0 to 1 minus y, that won't change. F of x, y, z, dz. I'm gonna leave that alone. I'll leave that as dz. And then we are gonna switch the other two. So this is gonna be dx, dy. All right, people, here we go. So go back to the picture in the xy plane now. And if I want to write dx, dy, then that means my limits for y have to be the constant limits on the outside. So that's going to be from 0 to 1. And then now my limits for x, notice in the x direction, I need to have the equation of the parabola on the left-hand side. So we know that x would equal negative rad y there. And then x equals positive rad y for the right half of the parabola. So those are going to be our limits. Negative rad y, positive rad y. Okay, that's ordering number 2. So this is using xy plane as the base. Okay, now what if we integrate with respect to x first? Which would mean I'm going to use the YZ plane as the base. Okay, well, what is the projection of this solid in the YZ plane? What does it look like? Well, notice we have z equals 1 minus y, and you can see that that's going to make a triangle in the YZ plane. I'm going to draw it separately for you. So here's our z-axis, here's the y-axis, 1, 1, and we're going to treat this as the base region over which the solid lives now. Okay, so this equation would be z equals 1 minus y, right? Intercept is 1, slope is negative 1. Okay, so if I'm going to use the YZ plane as the base, let's do this ordering in the same color. Okay, good. So then now from here, we are going to either have y or z as the outermost limits. Let's do y first. So limits for y are going to go 0 to 1. Limits for z, if you want to do that little arrow, right? So it starts at 0, ends at 1 minus y. And then now I'm going to have my limits for x. Okay, we'll look back at the solid, right? If we're treating the YZ plane as the base, what's determining the height of the solid in the x direction? Well, notice here, I'm going to draw another arrow. Notice here, it's determined in the x direction on the left by the parabola and on the right by the parabola as well. And so we're going to use negative rad y for the lower limit and then positive rad y for the upper limit. And then we have f of x, y, z, dx, dz, dy. Okay, good. And then let's switch the z and the y on the outside. So it's just going to go 0 to 1 still. And then this equation here, z equals 1 minus y, I'm going to solve it for y now. So y equals 1 minus z. So that's all that's going to switch. You have 0 to 1 minus z. And then the limits for x are the same, negative rad y to rad y, f of x, y, z. This is going to be dx, dy, dz. So good. All right, only one more left. Are you ready? Okay, so what's left? We're going to do y first. And use the projection of the solid in the xz plane as the base. Okay, so can you imagine what's going on in the XZ plane? If you were to project the solid in it, if you were to stand on the y-axis looking dead straight at the XZ plane, some people can see it. It's a little hard. It's a parabola opening downwards. If you can't visualize it, there's of course an algebraic way to find what it is. So we know that z is equal to 1 minus y, right? That's that plane up there cutting it. And we have that y is equal to x squared. So if I substitute in x squared for y, then I get z equals 1 minus x squared. And that's going to be what our base region is in the XZ plane. So I'm going to draw it out for you and then maybe take another look at the solid, and then you'll notice, oh yeah, that is what it looks like. So this is going to be 1, negative 1, 1, and it looks something like this. We'll shade this guy in. Okay, now look back at it. Do you see how if you were standing on the y-axis facing the origin, facing the XZ plane, you could see that parabola opening downward? All right, so we're going to use that as the base region. So let's first set it up easiest way. We'll have our outer limits for x, so those will be constant. So we'll go from negative 1 to 1, and then z is going to go from 0 to 1 minus x squared. And then what about the limits for y? Well, look at the solid again. You're going to really need this. So y starts, let me do a thicker arrow in red. So y is going to start at the equation of the parabola, and then it stops when it hits the plane. So look at the red arrow. The solid starts at the parabola, stops when it hits the plane. Actually, I don't like that arrow at all. Too chunky. So look at y. Y starts there, ends there. Y starts there, ends there. Starts there, ends there. So it starts at the parabola, ends at the plane. So what was the equation for the parabola? It was x squared. What was the equation for the plane? Well, y was equal to 1 minus z. And then you have f of xyz dy dz dx. It's going to bother me, that one came out too thick. Okay, very good. Now let's switch it up. Last ordering, we're going to have limits for z on the outside. So z is going to range, these have to be constant, from 0 to 1. X is going to range, notice, from the left-hand side to the right-hand side of the parabola, from there to there. So I have to rearrange this so that I have x squared equals 1 minus z. So x equals plus or minus rad 1 minus z. So the lower limit's going to be the negative radical, and then the upper limit's going to be the positive radical. And then keep the limits for y the same. So x squared 1 minus z f of xyz dy, and then this is dx dz. Good job. Those are tricky, but if you understand it, you should feel very accomplished. Okay, let's do something else with not so much reordering, huh? Let's set up the triple integral over e of z dv, where e is bounded by the cylinder y squared plus z squared equals 9, and the planes x equals 0, y equals 3x, and z equals 0 in the first octant include a sketch of the solid. All right, you got it. So let's see here. This cylinder, y squared plus z squared equals 9, it's opening along the x-axis. And then the planes x equals 0. All right. Y equals 3x and z equals 0 also cut it up. And we're going to sketch this solid right now before things get out of control. Okay. So we're in the first octant. That's reassuring. Y, z, here we go. So the radius is going to be 3, so I'll go up to 3 in the z direction and in the y direction. And I'm ready to project it parallel to the x-axis. So here we go. I'm only going to draw the portion in the first octant, so just from here to here. And then maybe we'll extend it to here to where x equals 3. I don't know. We'll see. Okay. Now other planes are coming in and cutting this thing. Let's see what's going on here. So x equals 0 is cutting it. Okay, that's fine. That's the YZ plane. So what does that mean for us? Well, that means this is one of the faces of our solid right here. Okay, the plane y equals 3x is cutting it. So I'm going to draw that. That's a line in the xy plane and then project it parallel to the z-axis. So y equals 3x, it's going to go through the origin. Slope is 1. So if I go rise 3 over 1, that's going to be right here. And so imagine a plane up and down. It's going to cut the solid into like this little wedge piece right here. Okay, and then z equals 0. So z equals 0 means we have the xy plane as a face of the solid. All right, so now all we have is this little wedge here. Let me draw one more little bit of shading. This is a little face coming towards us. Okay, it looks like a slice of a bundt cake or something, doesn't it? Maybe because I haven't had breakfast yet. All right, so here we go. What do they want us to do? Set up the triple integral. All right, they let us pick the order. So you guys get to pick the base region. What's making you excited? How about the XY plane? I think it's a good choice. All right, so XY plane is the base region. Always draw it separately, okay? It'll just help clarify things. Make sure you set up everything correctly. So X, Y. And then we have 1, 3, right? And then be careful, please, with what part you shade, right? Because that's going to determine whether or not you set this all up correctly. Okay, so you're gonna draw the upper half of this triangle, not the bottom half. And so this is bounded above by y equals 3 and below by y equals 3x. Yeah, did you get that? So I'll put limits for x on the outside. Those are going to be my constant limits from 0 to 1. And then limits for y, lower limit's going to be 3x, upper limit is 3. And then now what about the limits for z? We'll go back to your picture of the solid. I think this will be fine for you. So notice in the z direction, it starts in the xy plane, and then it's determined above by whatever the equation of that cylinder is. So I have to solve for z. Ooh, what a weird shape. Okay, so z is going to be equal to plus or minus the square root of 9 minus y squared. But since we're in the first octant, I'm just going to choose the positive radical. So I'll have 0 to rad 9 minus y squared. And then what are we integrating? Z. And our order is dz, dy, dx. And that's it. Beautiful. All right. Moving on, sketch the solid whose volume is represented by the following triple integral. So notice there's no function that we're integrating, and so we're using the fact that the triple integral of dv gives us a volume, right? Okay, well it looks like we're using the yz or the zy plane as our base region. So let's draw that out first. And then I'll throw in the height in the x direction. So y is going to go from 0 to 2. I'll say this is the y-axis, this is the z-axis. And then z is bounded above by the line 2 minus y and below by y equals 0. So this is the base region in the yz plane. And then notice this equation, 4 minus y squared, is an upper bound for x. So x equals 4 minus y squared. That's a parabola opening in the negative x direction. Okay, and it's gonna have intercept 4, 0, 0, and then 0, 2, 0, 0, negative 2, 0. So let's draw this whole thing out now. And I'll put this dead center because the whole point of the problem is just a graph, right? So showcase that graph. Okay, so let's draw our base region. That'll give us some sense of security perhaps, huh? This is 2. This is 2. I've got this going. I'll shade it in with this light color here. Beautiful. Okay, now the x-axis, I'm going to scale it out to 4. And then we have, ooh, I need a little bit of negative y-axis, don't I? But it's not going to be part of the solid. Okay. So we have this parabola, 4 minus y squared. It's going to intersect right there at 0, 2, 0, coming down here. Oh no, I need a parabola. Okay, great. And then notice z equals 2 minus y. That's a plane. That's cutting this parabola. So normally this parabola here, it would go upwards, right? You would project it upward and it would look something like this. But then that plane, z equals 2 minus y, cuts it. So what does that do to our solid? Well, basically, this will still come up to 2 here. And then the plane, since it cuts it, is going to take a slice out of the top like that and come across here. So we have this face, I'll shade it in for you here, towards us. And then also, this is a face of it, cut by the plane. Z equals 2 minus y. All right, very good. Those can be a little tricky to imagine. If it helps you, you could also draw 4 minus y squared and then cut it afterwards and just kind of imagine knowing that you have that base region in the YZ plane, what part you would have to cut off, if that helps you more. It's up to you how much erasing you want to do. All right. Let's look at another example. Next example says, use a triple integral to find the volume of the solid bounded by 4x squared plus z squared equals 4, y equals 0, and y equals z plus 2. So let's go ahead and start drawing the solid, and then we'll see what the best way is to set up the triple integral to find its volume. So let's see, 4x squared plus z squared equals 4, that's going to be an elliptic cylinder. And it's opening on the y-axis, right? Since y is missing. Y equals 0, that's just the xz plane. And then y equals z plus 2, that's another plane. That's going to be cutting or intersecting with this surface to bound our solid. So let's go ahead and sketch out what we have. And it's opening along the y-axis, so I'll put a little bit more in the y direction than normal. So we have this elliptic cylinder. In the z direction, it's going to go up and down 2 units, centered at the origin, 1 and negative 1 in the x direction. So let's fill that in first. Okay, and then I'm going to project this along the y-axis. So remember, you just want to pick a few points and add some consistent arbitrary distance. So what I would do is, I'm just going to copy paste this. That way my picture has good perspective. And you can always just use a ruler to make sure everything lines up well for you. Okay. So now let's connect everything here. All right, we'll live with it. Now, y equals 0 is also bounding this solid. So y equals 0, the xz plane, that's going to be back here. All right, so we've got this ellipse in the xz plane serving as one of the faces, right, of our solid. And then y equals z plus 2, that's a plane. Easiest way to graph it is just draw the line that it represents in the yz plane. So z equals y minus 2, right? So I could draw that line and then just project it parallel to the x-axis. And I know that the intercept on the z-axis is going to be at -2. On the y-axis, it's going to be at +2. And so it's going to cut through the elliptic cylinder. And you can imagine it's parallel to the x-axis, so I don't want to draw, we're going to project it parallel to the x-axis. I don't want to draw too much and make a really sloppy graph, but you know what, it should be a little, the angling should be a little bit better. Okay, when it slices, it's going to make like a rounded kind of face to our solid. So if you can imagine, there's basically 3 pieces going on here. So we have this face here that's being sliced by the plane, z equals y minus 2. Then we have this other face here, which is determined by the elliptic cylinder. This is coming at us all the way around and around on the outside, like outside of a soda can or whatever. And then that green ellipse in the xz plane, you could think of that maybe as the base. That seems like the most natural thing to designate as the base. All right. Good. If you want, you can always draw out what's going on separately. So this is in the xz plane, that ellipse. And then you have that top portion of the elliptic cylinder, and then it's getting cut by the other plane. So then it makes this kind of a face when it cuts it. Okay. All right, so let's draw the base region, which is in the xz plane. Yes, it is. Separately. That way we can figure out what the appropriate limits of integration should be. So I'll draw the z-axis here, x-axis here, and we just have a little ellipse. All right, so in the z direction, we're going to go up and down 2 units. In the x direction, 1 unit. Yes, if you need to, right, remember to divide everything by 4. So you would have x squared over 1 plus z squared over 4 equals 1. So let's draw this ellipse. And it makes sense. We'll set it up so that the constant limits are for x, and then we'll bound the region above and below in terms of z. So since I know this is z squared equaling 4 minus 4x squared, the upper half is going to be positive radical 4 minus 4x squared. And the lower half is going to be negative radical 4 minus 4x squared. Good? Okay, we're almost ready to roll. So let's set up the limits that we have. So in the x direction, the volume, the bounds are going to be from -1 to 1. In the z direction, from negative rad 4 minus 4x squared up until positive rad 4 minus 4x squared. And then what about the y direction? All right. We'll go back to your original drawing and then draw that arrow that starts and stops in the y direction, representing the height of the solid. So notice it starts where y is equal to 0 in the xz plane, and then it stops at that plane that cut the elliptic cylinder, z equals y minus 2, or in this case, since these are limits for y, I'm going to use z plus 2 as that upper limit. Okay? So lower limit 0, the xz plane. Upper limit is going to be z plus 2. And then don't forget, this is for dy, dz, dx. Bravo. All right. Last one. We're going to end with a bang, okay? So hang in there. So this figure shows the region of integration for the following triple integral, and they're not telling us what f of x, y, z is. They're just saying, using the xz plane as the base, here are the limits, and then y is the height of the solid, so from 0 to 1 minus x. rewrite the integral using the other 5 possible orders of integration. All right, so I'll start off with the easiest reordering. I'm just going to interchange z and x as they're written. So first let's see what the base of the solid is in the xz plane, what its projection is. So notice here, the limits for x are from 0 to 1, and the limits for z are from 0 to 1 minus x squared. So this is z equals 1 minus x squared. You can see that right here. And this is the region of that solid in the xz plane. So now I want to interchange it, meaning I want the outer limits to be for z, and then I want to write x as a function of z, or x in terms of z. So that means I would have x squared equals 1 minus z, and I'm going to choose the positive radical since we're in the upper half, so rad 1 minus z. So here we go, we already have one reordering. So limits for z are going to be from 0 to 1. Limits for x are going to be from 0 to rad 1 minus z, and then I can leave everything else alone. So 0 to 1 minus x, I didn't mess with that. F of x, y, z, dy, and then now this is dx, dz. All right, we survived that reordering. 1 down, 4 to go. Moving on, let's switch what we're going to use as the base of our solid. Let's integrate with respect to z first, meaning we're going to use the xy plane, or the projection of the solid in the xy plane as the base. All right, here we go. So in the xy plane, what is going on? I see a triangle, right? Draw it out, draw it out. So here's the y-axis, here's the x-axis, and then y equals 1 minus x is bounding the region. They wrote the equations out for us and everything. I'll shade it in purple, and then I'll match it up to the solid for you. It's this part right here. Okay, good. So here we go. The 2 orderings are going to be pretty straightforward. If we have x on the outside, x is going to be bounded by 0 to 1. Y is going to be bounded below by 0, above by 1 minus x. Now what about z? So go back to the solid, okay? And then look, if you're using the xy plane as the base, and then you're trying to see what's determining the height of the solid, it's this curve right here, 1 minus x squared. So you're going to go from 0 to 1 minus x squared, f of x, y, z, and then this time we did it dz, dy, dx. Okay. I don't want it to get too messy. And then very easily I can just interchange the last 2. Let me scoot this guy over, scoot, scoot. So now if I have y on the outside, again the limits are going to be from 0 to 1. This time I need to solve for x in terms of y. So x equals 1 minus y, pretty much same thing. So I'm going to go from 0 to 1 minus y in the x direction. And then z is the same. So 0 to 1 minus x squared, f dz, dx, dy. All right, woohoo. So far, you're like, this is smooth sailing, right? I saved the best for last. So now we're going to integrate with respect to x first. So the outer limits are going to be y and z. I'm going to use the projection in the yz plane as the base. Now, hopefully you notice, you're going to have to split this into 2 integrals. I'm going to draw what's going on in the yz plane. You might be all relaxed thinking you just have a square, but alas, you do not. So here we go. In the yz plane, yeah, it's a square, but we have to cut it into 2 pieces. Z-axis, y-axis, 1 to 1. All right, but then notice for part of, remember we're using the heights of the solid in the x direction. So for part of it, I don't think you can see that color. Let's do something more fierce. So for part of it here, 1 minus x squared is determining the height, right, in the x direction. So I would maybe cut it here, and I'm going to shade that portion into with green to correspond so you can see. And then on the other half here, it's 1 minus x that's determining the height. Okay, so we have to split the base region into two portions. So this is going to be region 1 and region 2. Now, how do I know exactly where to split it or how to split it? So what you want to think of is what's going on in the YZ plane here. All right, now I know the height here is determined by z equals 1 minus x squared. I want to know where does that intersect with y equals 1 minus x. Okay, so what I'm going to do is use substitution. So we have z equals 1 minus x squared in this portion, and then y equals 1 minus x in this portion, which means that x is equal to 1 minus y, right? So I'm going to substitute that in for x into the other equation, which means z is equal to 1 minus y squared. And that's going to be where the intersection occurs. So that would give me z equals 1 minus 2y plus y squared. So I get z is equal to 2y minus y squared. All right, so that's the curve of intersection right here. That is z equals 2y minus y squared. So we're going to split it up right now. Okay, you ready to roll? I think we can handle this. I'll do limits for y on the very outside first, okay? So constant limits for y. Y is going to range. We'll do region 1. Region 1. So y has to range all the way from 0 to 1, right? Z is going to range from that curve up until 1, yes? So from that curve, which is 2y minus y squared, up until 1. And then what about x? So x is the height of the solid, using the YZ plane as the base. So notice it's going to start at 0, and then it's going to come out to z equals 1 minus x squared, except I have to solve for x. So that means x squared equals 1 minus z. So x equals, I'm going to use the positive radical because where positive x values exist, so rad 1 minus z. So we're going to go from 0 to rad 1 minus z. I have f, this is dx, dz, dy, plus, and then now let's do region 2. So what are the bounds on y for region 2? Again, it's still from 0 to 1. What are the bounds on z? So z is going to go from now 0 to the curve 2y minus y squared. And then what about the limits on x? So go back to your solid. So in this portion here, I'll switch to pink. X starts again at 0, but then it's determined by this equation here. Again, I want to solve for x, so that means x is equal to 1 minus y. So that's going to be my upper limit. So we're going to go from 0 to 1 minus y, f, and then you have dx, dz, dy. Okay, that's one ordering. And then what's our other option? You guessed it, we're going to switch y and z at the end. Okay, or, so now these limits have to pertain to z. So for the z direction, if we're dealing with, let's do region 1 first. So region 1 in the z direction goes from 0 to 1. Now what about in the y direction? Well, it's going to start from 0, and then it ends at this curve right here. But I need to solve for y. My goodness, you might think it's a nightmare, but no, go back to right here. So I could solve for y in terms of z pretty easily. So I'm going to have z minus 1 equals negative 1 minus y squared. And then I'm going to have 1 minus y equals square root of 1 minus z plus or minus. And then I'm going to subtract 1 over and then multiply by a negative. So I get y equals 1, and then that'll switch to minus plus rad 1 minus z. So which one am I going to choose? I'm going to choose the negative, right? Because we're up in that portion of the yz plane. So we're going to go from 0 up until 1 minus square root of 1 minus z. And then nothing changes for x, okay? So you already did all the dirty work there. So you could just keep 0 to rad 1 minus z for region 1, f, dx, dz, dy, plus, and then for region 2, I'll do it below so that we're not running out of space. So this is for region 2. So limits for, oh, I'm sorry, it should be dy dz. I wrote it backwards. Dy dz. And then limits for z in region 2, again, are from 0 to 1. For y in region 2, notice it's going to go from the curve up until 1. So this time you're going to go from the curve from 1 minus rad 1 minus z up until 1. And then limits for x stay the same as they were for region 2 before. So 0 to 1 minus y. And then you have f dx dy dz. That one's definitely a doozy. Okay, but it's a great mental exercise, you know. So that concludes the lesson on triple integrals. Stay tuned, we're going to switch it up and go into different coordinate systems.